Hello everybody. I'm going to take some time now to go over some of the material for week 2 of our Statistical Concepts class. So looking at section 2.1, chapter 2 here, section 1, we're looking at different ways of organizing data, and we're looking at qualitative data for this section. That's that categorical data. So we're going to look at organizing it in a table, which is called the frequency distribution, and then two of the types of graphs that we look to organize are qualitative data. So first, we're going to look at constructing a frequency distribution, which is the first step. No matter what type of data we have, the first step in organizing is going to be to create a frequency distribution. So the frequency of a category is the number of times it occurs within that data set, within that sample. Frequency distribution is just a table that organizes those frequencies. So we start out with the raw data. Here we have 15 customers, and we want to look at what it is that they are, what type of computer they're buying. So the start of our frequency table is to just list out all the possible responses like we did here. That's the type of computer: desktop, laptop, notebook, tablet. Those are the 4 categories that are going to be appropriate responses to the question we're asking. They are the responses to our variables, or the different possible outcomes for our variable. And then you can see here we do tallies. We go here, okay, tablet, put 1 after the tablet. Laptop, 1 after the laptop. Oh, 1, 2, 3, 4 more laptops. 1, 2, 3, 4 more, and so on. Oops, there's another laptop. Notebook, desktop. So I've got a notebook and a desktop. And you can see they've already got the tallies there, so I'm not going to keep going. Now those tallies are a temporary column. It's there to help us form our frequency table, but it's not going to be part of our final frequency table. Once we've done all the tallies, our formal frequency table will look like this. We have the name of our variable here, saying type of computer, then all of our different possible responses down that column, our different categories that you can be put in. And then from the tallies, we've counted up the tallies, and we've got the actual frequency as a number. So this is the actual frequency table without the tallies in it anymore. From that, now with only 4 different responses here, only 4 different categories, it is relatively easy to look and say, hey, laptops are the most common, tablets are the least common. The frequency distribution makes it easy to see exactly how many observations there were for each category, how many responses were put in each category. But if there were more than 4 responses, it might be hard to, it might take a while to go through and pick out which one was the most popular, which one was the least popular. With 4 of them, like we had here, yeah, it's pretty quick to find the highest and the smallest number. But let's say if there were 12 or 13 possible categories, it would take some time. So we'll look at that in just a little bit, how we would make that quicker with our graphical displays, our graphs. The portion of observation in each category is called the relative frequency. So what we have up there right now, these are what we call the raw frequencies. They just say how often it occurred. Relative frequency is going to go a step further, and we're going to figure out basically what percentage or proportion of the time that it happens. A proportion is just the decimal form of a percent, sometimes called just a rate. So and you can see here the formula for that is just the frequency for a category divided by the sum of the frequencies. In other words, the total sample size, or the total size of the group that we're studying. In other words, that would be little n. So here, this is our table, our frequency table. The first step in doing relative frequencies would be to add these up. I believe that adds up to 50. So if you want to do a relative frequency, this would be 11 divided by 50, 0.22. This would be 23 divided by 50, 0.46. 9 divided by 50. You can see it's just each frequency divided by the total. Gives you the relative frequency distribution. And here they'll show, add up to get the total, divide each frequency to get the relative frequencies. So now that we can construct a frequency table and a relative frequency table for qualitative data, There are two main types of graph that we develop with qualitative data. Bar graph and a pie chart. Let's look at the bar graph first here. So the bar graph is just a graphical representation that shows rectangles, usually vertical in statistics, but we will show you an example of a horizontal bar graph. Some textbooks say that horizontal bar graphs are for display and advertising, not for statistical analysis. They're okay. It's just we're so used to seeing things done vertically. It's just less of a transition. So here's our table again. We got our frequency and our relative frequency. To construct a bar graph, we're going to just make our axes, and we're going to put our categories along the bottom. So desktop, laptop, notebook, tablet. Then we have to construct the axis up the side here. This axis has to go up to at least our largest number. So our largest number is 23, so I might do 5, 10, 15, 20, 25. So I'm up to just past my largest number, so there's more than enough room. So you can see here they have that graph made. They also made a bar graph of the relative frequency. Some textbooks have a special name for this, others don't. It's just a relative frequency bar graph is the simplest name for it. And you can see going up the side here, instead of having the raw frequencies here, they have the relative frequencies. So they have to go up to at least 0.46 because that's the highest relative frequency. They go up to 0.5. You can see the bars are exactly the same size on each one of them. The only difference is the way this axis, this scale is labeled here. Another thing you'll note, you'll see the bars have space between them. That is important. We want that space between them because it's relevant, because there is no connection between those categories. So that space is kind of visually representing that lack of connection. Now I'm going to flop to Excel here quick. I'm going to bring this information over, and I'm just going to show you very quickly how you'd make a bar graph in Excel. So, type of computer, desktop, laptop, notebook, and tablet. Frequency, I'm just going to fill in 11, 23, 9, and 7. Okay, so expand this back out. So I have this table here. Now I could dress this up with borders and stuff to make it look more like a table, but I don't need to because my goal here is to make a graph. So I'm going to highlight my table, and I'm going to go to Insert. Now bar graphs in Excel are always horizontal, what they call a bar graph. So the statistical bar graph, the vertical bar graph, you have to use a column chart. So I go there and I'm just going to select the first one, 2D column chart. And there it is. I have it. I don't need the key here, that legend, so it doesn't tell me anything. So I'm just going to delete that. And there we go. We have a bar graph. Again, Excel calls it a column chart. If I want to do my relative frequency, I would do a total here by using the sum function. Get 50, so this is going to equal this divided by 50 and fill down. By the way, if I did the sum of that, that better come out to be a sum of 1. My relative frequency better add to 1 or 100% if you convert them to percents. Now I could graph that as well if I wanted to. I'd hold down Control and highlight. And you can see it looks very similar, almost exactly the same as the other one, only the scales up the side is labeled differently. Yep. You can see that scale is labeled differently as well. Okay, back here. So sometimes it's desirable to construct a bar graph in which the bars are in order of highest to lowest frequency. That is sometimes called a Pareto chart. So from the same information, notice now we don't put the bars in the order they are in the table. We put them from highest frequency, laptop, desktop, notebook, tablet. So we're from longest bar to shortest bar. trying to think of an application where that's necessary. Really not coming up with one right now, but in statistics, oftentimes we want to compare the highest frequency of one survey or one situation to the highest frequency of another, so that would be where that would be used. Now, horizontal bar graph, like I had mentioned earlier, I'll just show you an example of that quick. So I'm going to give you another set of data here. Let's say what type of area you're employed in, whether you're in farming or forestry, fishing, manufacturing, mining, transportation, managerial or professional, office and sales, or other. And they jumped right to the relative frequency here instead of giving you the raw frequency. Remember, the shape of the bar graph will be the same. So then this time they put the categories on the side, and then they put the number scale across the bottom. Same thing. This number scale has to make sure you go up to at least the largest number in the frequency, relative frequency. So in this case, you have to make sure you go to at least 0.373. They make it up to 0.4, so there's more than enough space. Sometimes we want to compare two situations. So we have this information. Maybe we want to compare 1 year to the next, or one country to the next, but with the different items within them. And that's what we call a side-by-side bar graph, or sometimes called a double bar graph. So here we're looking at website use: Facebook, Google, YouTube, Microsoft Network, and Yahoo. And we're looking at February 2009 compared to February 2010, and this is the number of users, millions of users that have used those sites or hit on those sites. You can see here now, the blue is labeled 2009, and that peach or cream is 2010. So you can see Facebook had a significant increase in use from 2009 to 2010. Google and YouTube both had a good increase. MSN and Yahoo both stayed pretty stable. Yahoo looks almost exactly the same, and MSN looks like it maybe barely made a little bit of a change. Now, one of the weaknesses of a graph, if you asked exactly what was the usage in 2010 for Google, well, I trace that over here. I can't tell exactly. I can tell it's in the high 130s, between 135 and 140 million, but I can't get an exact number. If I want an exact number, that's where we come back to the tables. The tables are a little slower to find the information, but we can get more exact information. The graph, it's quicker to find it. I can very quickly find that Google is the most common, or that Facebook had a large increase, but to find exact values from that is tough to do. Let's take a look now at pie charts. A pie chart, we're looking at, again, categorical data. Once upon a time, they would have you calculate the number, the percentage of the data, the relative frequency, and use that then to find how many degrees out of 360, and then take a protractor and measure it out. Now with modern technology, we don't need to do that. I mean, the technology will do it for us if we want it that exact. But just know little basics like 25% is a quarter of a circle. So if you got something that's close to 25%, it's going to be close to a quarter of a circle, and so on. So going back to our laptop data, we're using the relative frequency. They construct a pie chart here. I'm going to show you how to do one in Excel quick. So here is our data. I'm just going to go to Insert, Pie Chart, and Standard 2D Pie Chart. And there it is. Now all my information is out here right now. I'm going to get rid of that once. Go to Insert, Pie Chart. Now I'm going to select this one here, and I'm going to see if I can change some of my options. Add data labels, that puts the numbers in there. I can format my data series a little bit, and it'll ask me what I want to put in it, what I will use. Border styles, shadow effects, series options. There's no format legend. I can change different things on my legend. Trying to remember how to get it to put the words right in the chart and get rid of the legend, and I'm not remembering it right now. there's an include data labels, and I'm not finding it at the moment. But anyway, you can play around with that. There are instructions in the book for adding the data labels and all that stuff. So those are our pie charts. So we've learned how to create a frequency table for qualitative data. We've learned how to make a bar graph, and now how to construct a pie chart. So that is everything for unit chapter 2.1. So I'm going to switch over to the other PowerPoint now. I'll be back in just a second. Okay, now then for section 2 here of chapter 2, we're looking at frequency distributions and graphs for numerical data or quantitative data. So we're going to be doing the same thing, frequency distribution for quantitative data. A bar graph now for quantitative data is called a histogram, and we'll go over some of the differences. Shape and distribution of histograms we'll talk about, and frequency polygons and ogives. So let's look at the frequency distributions. Now before I get into the example in the PowerPoint here, I do want to remind you, frequency distributions or quantitative variables have two types, discrete and continuous. Discrete variables sometimes have a small enough number of possibilities that we can get away with doing them almost exactly like we do with our qualitative data. For example, if I ask, how many classes you have this semester. I mean, if you have 0 classes, you're not a student, so that's not possible. So number of classes, you might have 1, 2, 3, 4. Let's say that nobody surveyed had more than 4 classes. And I'm only saying that because I'm out of room. You have your frequency, and you list their frequencies. So we have them listed like that. We can go ahead and make a bar graph or actually a histogram off of that just out of those data. We can just list individual values because there is a small enough number of discrete values that we can just list them out as our category, almost like our categories. So what we're going to be looking at mostly in this section is where we have to do a different strategy, which is usually for continuous variables or a discrete variable. We have a large number of possibilities. For example, let's say we're looking at city populations. Well, you can't possibly list out all the different possible values from, let's say the smallest city only has like 18 people up to a large city with several thousand. That'd be a huge list here for my population number. I don't want to do that. So what we do is we end up grouping it. So like this here. Here we have classes. We're going to list from 0 to 4, 5 to 9, 10 to 14, 15 to 19. We're grouping them together because we can't possibly list out all the individual possible values. And even if we did list out all the individual values, the chances of any single value getting more than one occurrence would be very, very unlikely. So the frequency table would be kind of useless. It'd be a bunch of zeros and ones in our frequencies. So we make those intervals, those groups or classes, we call them. And those classes have some items we'd like to do. First of all, class width. Each class has a lower limit and an upper limit. The first number is its lower limit, top number is its upper limit. The class width is the difference between the lower limit of one class and the lower limit of the next class. So you can see here that 0 to 5, 5 minus 0 is 5. And that should be the same for all of them. 10 minus 5 is 5. 15 minus 5 is 5. So we have a class width of 5. Now also you could find the class width by subtracting the lower limits. 9 minus 4 is 5. 14 minus 9 is 5. 19 minus 14 is 5. So you can double check that consistency to make sure it's consistent. So here again is just a review. The lower limits are the first number in each class. The upper limits are the second number in each group. The upper number, and the class width is just the difference between the lower limit of one class to the next. So, some rules about our classes. The tough parts of these is actually making those classes. I mean, here we just gave them to you so it don't look so tough. But if you have a set of data sitting in front of you, figuring out what those classes needs to be can be tough. First of all, we don't want the lower classes to go way below the values of the data. We don't want a bunch of empty classes at the bottom. So I'm going to add that to the top here. Avoid empty classes. If I can spell, maybe. Try that again. Avoid empty classes at bottom. At the lower end. It's at the top of our table, but lower end of the data. Every observation must fit into one of the classes. So this set here that we had 0 to 4, 5 to 9, that'll only work if our observations are only measured to the closest to 1. If they're measured, if it's possible to have 4.5, these classes don't work because 4.5 would fall between classes. We can't allow that. Each observation must fall into a class. It cannot fall between the classes. And there cannot be any chance of it falling between the classes. So if we're measuring to the nearest tenth, even though we might not have anything between 4 and 5, we can't have that opening there. So we would have to go, instead of 0 to 4 and 5 to 9, we have to go 0 to 4.9 and 5 to 9.9 and 10 to 14.9 and so on. That way there would be no chance of a data value falling in between them. Even if we don't have any values in our data set that fall in those gaps, we still have to design those classes so that if we gather more data, there's no chance of any of the new data falling in those gaps either. Next, the classes must not overlap. Some people might say, well, what if we go 0 to 5, 5 to 10, 10 to 15? Well, then which class, if we do have a value that's exactly 5, which class does it go in, the 0 to 5 or the 5 to 10? That's an overlap. We cannot have an overlap. They must be equal width. We've discussed class width. That has to be the same. From lower limit to lower limit of one class to the next must be the same all the way up. And again, no gaps. So no gaps between classes. General steps for constructing them. One, we choose a class width. Now, they're being kind of nonchalant about this. A lot of times you decide how many classes you want to have. Let's say you decide you want to have 6 classes would make your graph look the best. So then you look at the range of data and you adjust from there. You know, your range would be your largest minus your smallest. And you look, okay, so you get, let's say your largest number is 60 and your smallest number is 25. That gives you a range of 35. Let me write that out. So you got 60 minus 25 gives you a range of 35. If you want 6 classes, you divide by 6. That's going to give you 5.83333. So that's telling me, I'd say maybe a class width, round that number up generally. So a class width of about 6 might work here. So then you put the lower class in a convenient spot just slightly smaller than the minimum data value. So if I'm using a class width of 6, I'd probably, here 25 is a convenient data value. I'd start at 25. So do 25 to, now remember, the next class has to start at 31, which is 6 more than the previous class. So I might end up at 30.9 or 30.99, depending on what my data looks like. Compute the lower limit for the second class by adding the class width to the lower limit for the first class. So that's what we were saying. If our first class is 25 to something, if we're going to use a class width of 6, we take 25 plus 6 is 31. Now we can go back and decide where this first class is going to end. If we're going to the nearest 10th with our data, then this would have to be 30.9. If we're going to the nearest 100th, that'd have to be 30.99. If we're going only to the nearest 1, we might get away with just saying 25 to 30. So compute the lower limits for each of the remaining classes. So you'd keep adding, here if we're using a class with a 6, so we go 31, 37, 43, and so on. And then you can go back and fill in all those upper limits for each. Then go back, just like we did with the other frequency tables, you have to count the number of observations in each class. You can use the tallies, again, if you wanted to, or just count them up. I tend to use the tallies just because it keeps me from making mistakes as I'm counting them up. So let's say we got data looking like this. Construct a frequency distribution with a class width of 1. Now first we got to look, we do have numbers smaller than 1, and we're going to the nearest 100th. So if we're smaller than 1, a convenient grouping here would probably be to start at 0 and go to 0.99. Now I kind of jumped the gun with that 0.99. If I have a class width of 1, if I start out at 0 here, the next one has to start out at 1, next one at 2, next one at 3, and so on. Going up by 1 from one lower limit to the next lower limit. So then since this goes to the nearest hundredth, I have to go to 0.99 to make sure nothing squeezes in between. So this has to be 1 to 1.99. Again, I have to get as close to that 2 as I can. I'm going to the nearest hundredth in my data, so I have to be within a hundredth of the next lower limit. So within a hundredth of the 2. The next lower limit would be a 3. I didn't have room on the bottom there. So I'd have to go from 2 to a hundredth less than 3 is 2.99. So you look at the data and what it's measured to, that decimal place, that tells you how close you have to get to that lower limit with your upper limit for the previous class. So class width is given as 1. Smallest value in the data is 0.25. A convenient number lower than that would be just 0.00. So they're using that. So the next lower limit would be 0 plus 1 or 1.00. So that's where we get all their next lower limits. We add 1 to get 2, add another 1, add the class width each time to get 3, add another 1 to get 4. Again, adding that class width each time to get the next lower limit. And there's exactly what I was describing. So you go from 0 to 0.99, 1.00 to 1.99. Now I just did 1 to 1.99. Technically, if we're looking at measurements and talking about significant digits, you should have 1.00 to 1.99 because the 1 is just implying a round off error. So 1.00 is implying the necessary precision. I'm not going to be really picky about that on a test. So then you count up the frequencies like we did here. You can also make relative frequencies just like before. Remember, we added up the total frequency to get a total, and we divided each frequency by that total to get the relative frequency. So now that we have that frequency table, how do we make a histogram? Well, histogram is exactly like a bar graph, only along the bottom of our histogram, instead of having categories, we have those ranges. 0.00 to 0.99. 1.00 to 1.99, and so on. Once we have a frequency distribution or a relative frequency distribution, we can put the information in graphical form by constructing a histogram. So there it is. Our class width goes down on the bottom. Our height is our frequency, or we could use relative frequency. Notice these bars are tight together. There's no space between them. I pointed out in the bar graphs that there was space between them. That's because there, between laptop and tablet and whatever, there was no connection between those. There were discrete, separate items, categories. Here, this is 0 to 0.99, and this is 1.00 to 1.99. These class widths, they do connect to each other, and one flows naturally into the other. So it makes sense that they touch, that they are connected on the graph because they are connected numerically. So back to our frequency table, we'll show both the raw frequency histogram and the relative frequency histogram. Again, you can see the bars are tight together. And sometimes they will do this rather than label. Here you can see what they're doing is they're just putting the lower limit of each class at the border, which is fine. The way I was always taught was you put the range here. This is listed as 0 to 0.99. This is listed as 1 to 1.99. And 2 to 2.99. And so on. You put that range, that class or group in there to describe them. But again, some books will do this. They just list the lower limit at the front of each bar and at the boundary between the bars after that. How do you know if your class width was correct? Well, this one here, you can see it's really jagged, a lot of narrow bars. That class width was way too small. It gives me the same general shape, but a larger class width, like these, gives me a much more descriptive shape. Or you only get the most basic features of the data. You don't get any ups and downs. You just get the big blobs. That's saying our class width was too large. We need to make it smaller. Okay, how do we make a histogram on the TI-84? So you enter your data into L1. So I'm going to go back to my data here. That's slide 18. So here's my data. If I have my calculator up, put it over here for now. I'm just going to enter it in by the count. So I go to Stat, Edit. You see I get L1, L2. I'm going to clear out my list here quick. I'm going to arrow up to highlight L1, hit clear and enter, and it'll clear out the whole list. I'll do the same with L2, clear and enter, and L3 just to clear out my list register here for now. So I arrow over to L1. So I've got to put in these numbers. So 1.5, enter, 1.48, enter, 1.4, enter, 3.12, enter, 0.25, enter, and I'm going to keep going. Now I'm not going to put all these in. I'm just going to put in the first couple of columns here. Roll one more column. So 1.12, 1.06, oops, 1.11, I jumped columns there, 1.81, 2.12, and 3.36. So that's going to be enough. I'm just going to have those first 15 items in there. Now I'm going to go back here to where I was at. So we're going to say that I've put them all in there. Now you're going to press second and y equals. You see there's the y equals up here. Above it is stat plot. So we're going to second, and what we're doing is we're going to stat plot. So we're going to choose option number 1, and it takes us into that one. Access plot 1. We're going to turn it on, so we're going to hit enter there in the on. Our type of plot, we're going to arrow over here to histogram, hit enter. Our X list should be L1. Our frequency, for everything we do, frequency is always going to be 0. The only time we'd change that is in some upper level statistics when you're weighting things. So for us, that's good. So we're going to press zoom, and 9 is going to take us to a table of the data. Maybe. So let's go X list at which other again. 1. So it's in there. So exit out of that. Then I'm going to do zoom 9. Let's see if we do it. So there's my histogram. Now I can trace if I want to. Hit the trace button. I can jump from one to the next. Here I can see that that is a value of 0.25. That's a value. So I'm sorry, this is 0.25 to 0.872. So this is the lower limit of this class is 0.25 to 0.872. This goes from 0.872, again, bad form. They shouldn't overlap like that. But from 0.872 to 1.494. You can see the way it gets away with either less than here instead of an equal to. So it's actually 0.872 to anything less than 1.494. The next bar goes from 1.494 to anything less than 2.116. So you gotta be careful. The calculator uses some funny notation different from our book, but you do have a histogram. Now setting the widths of these can be a little tricky. We're not gonna mess around with those for now. Right now that's gonna be basically what you have. So anyway, let's take another look at another example here. It is sometimes necessary for the first class to have no lower limit, or for the last class to have no upper limit. Like this one here, we're saying 85 and older. Statistically, that's a little sloppy because you like your classes to all be the same size. You could have the lower limit could be the same as, you know, up to 14 instead of 5 to 14. Again, the range of that class is now bigger than the others, and like up here, 85 and older, that's the largest number on our table. Well, is that really the largest number because there's a lot of people there, or is that the largest number because We've got a larger class width. Instead of going from 85 to 94, we're going from 85 on up to however old. So is that why that number is larger? Since we're talking about deaths, generally, yes, over 85 would probably be the highest rate anyway. Here, we're looking at discrete data. So as I was mentioning before, we could list out the values one at a time. We don't have to have ranges, get their frequencies, and then when we make our histogram, we don't have ranges down here, we just have single numbers, 0, 1, 2, 3, 4, 5. So let's look at the shape of a distribution from a histogram. Here, this one, if I'm looking at the top of the bars, it's kind of like a bell curve. That bell curve is a shape that we call the normal distribution. We're going to talk about normal distribution with normal probabilities and normally distributed data a lot during the course of this class. It's also symmetrical. If I folded it down the middle, this side would fit onto the other side symmetrically. This is skewed. The direction that the tail goes out is the direction it's skewed. So this is skewed right. This has the longer tail to the left, so this is skewed left. Now these are drastic skews. I mean, a skew could be a little more subtle. This one's also skewed left because the tail is stretched out to the left. This one would also be skewed right because the tail is stretched out to the right. So we also have the modes. Unimodal has only one most common that comes up to a single peak and back down. Bimodal would have kind of the two humps to it. We'll talk about modes a little bit more next week. Look at the frequency polygons and ogives. Frequency polygon, oops, didn't jump down there. We're going to represent the frequency, the relative frequency of a distribution. And all we're going to do is the class midpoints. The class midpoint is the lower limit of one class plus the lower limit of the next class divided by 2. So we had from 0 to 4 and 5 to 9 and whatever. We would use 0 and 5. Let me write this out. So we had classes of 0 to 4, 5 to 9, 10 to 14. To find the midpoint of this class, we would take its lower limit and the lower limit of the next class. 0 plus 5 divided by 2 is 2.5. So the midpoint here would be 2.5. Would be that class midpoint. So then histograms are the most common representation, but sometimes they use something called a frequency polygon. It is constructed by plotting a point for each class instead of the bars. So the point is going to be at that midpoint for the x-coordinate, and the frequency will be the y-coordinate. So here's our classes. There's the frequency. First, we've got to find the midpoint of each class. So it'll be 0 plus 1 divided by 2 would be 0.5 would be that midpoint. So you see 0.5, 1.5, and so on for our midpoints. So now what we're going to do is we're going to draw a scatter plot, basically, where we have 0.5, 1.5, and then up here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Probably go 5, 10, 5, 10, 15, 20, 25, 30. 0.5 is going to be at 9. 1.5 is going to be at 26. 2.5 will be at 11, and so on. And here is our frequency polygon. What this shows us is, okay, from the first class to the second class, we're going up rapidly. From the second to the third, we're going down rapidly. Third to fourth, we actually have a slight rise. Then we continue to decrease after that until we get to that last class. Relative frequency polygon. We use a relative frequency instead of the raw frequency. This was the raw frequency. This one is the relative frequency, that proportion or decimal. Ogives and cumulative frequency. Well, an ogive is just, we take the cumulative frequency of the frequency table and we graph that as kind of that line graph. So the cumulative frequency, we take the raw frequencies and we're going to alter it a little bit. Instead of going from 0 to 0.99, we're going to list anything less than or equal to 0.99, which is the 9. This one, instead of going from 1 to 1.99, is going to be anything less than or equal to less than or equal to 1.99, which includes these, but also these. So that would be 26 plus 9, or 35. This one would be less than or equal to 2.99, which include all those plus the 11 more, 46, and so on. So there you can see them. So even though it's still listed as these classes, it includes everything in that class and anything less than the upper limit of that class. So that class and all the ones below it. This top number here better be our total frequency, which it would be. If we added up our frequencies, we'd get 65. So we plot that using our upper limits, not the midpoints anymore, but the upper limits for the cumulative frequency, and that there forms our ogive. You could also do a relative frequency ogive, which is the same thing. It's a cumulative frequency divided by the total frequency, or we could take the relative frequency and add them up to accumulate up to 1. So that's it for our numerical data. We did our frequency tables, both grouped frequency tables and then the individual value for discrete data. We did histograms, both raw frequency and relative frequency. Talked about the distribution, modal, bimodal, normal, and so on. Constructed frequency and relative frequency polygons and ogives. Remember, polygons use the midpoint of the class, and ogives use the upper limit of the class. Okay, that is all the information for section 2 of chapter 2, so I'm going to pause and pull up the next PowerPoint. Okay, so in section 3 of chapter 2, we're looking for more graphs and more on quantitative data. So we're going to look at stem and leaf plots, dot plots, and time series plots, or a more formal line graph. So our histograms that we've looked at show that frequency distribution, frequency table. For small data sets, however, sometimes going through a histogram is not adequate. So we can do, for data sets that have fewer numbers, we can do stem and leaf plots. So let's look at a stem and leaf plot. Stem and leaf plot involves us looking at the data and basically pulling off the first digit of the data and making that into your stem. So if your numbers go from somewhere in the 20s up into the 50s, your stem will be 2, 3, 4, and 5. That represents 20, 30, 40, and 50. And then the ones digit goes in your leaves. So here we're showing decimal numbers. 14.8, 14 could be your stem, and the 8 could be your leaf. The last digit is always your leaf. The stem is the first digits. You can never have more than one digit at a time in your leaf. So you make a vertical list of the stems in order, increasing order, and then draw that vertical line and put all your leaves in. Then we have to come back and put the leaves in order. So here is the population of several U.S. states. Notice they're close to the same. So we can list them starting, I believe it looks like 10 million. So 10, 11, 12, 13, 14. I have to go up to 15. Do we have 16 in there? So our our stems, we would have 10, 11, 12, 13, 14, 15 would be our stems. And I don't see any 16s, so I don't think we have to go up to 16s. Like Alabama's 14.1, so we put a 1 after the 14. Arkansas is 14.3, we put a 3 after the 14. 14.4, a 4. 17.8, oh, I do have to go. I got to have 16 and 17 here. 17.8, I have to put an 8 after the 17 because it's a 0.8. 12, no, there's no decimal there, so I got to put a 0 after the 12. Count that as 12.0. 14.9, I put a 9 after the 14. Now notice these may not be in order right now. They most likely won't be. We'll have to come back later and put them in order. So we'll see here, they just took them like I was doing and got them all put in here for this one, in this spot. And then they came back and they put them in each line, they put them in order from smallest to largest going that way. And so you can see that for each of them. Now a couple of things this does for us. This is almost like making a histogram. You know, this is really saying from 8 to 8.9. And this is saying from 9 to 9.9, from 10 to 10.9. And you can see the group that has the most, because it goes over the furthest, almost like the longest bar, is the 13, which really is 13 to 13.9. So that range has the most values in it. The nice thing about this is not only do I get that length effect if I do it right, so that longest line is the highest frequency, but I also get all the individual values are listed there for me as well. We can make a back-to-back stem and leaf plot to show two values at once. Here, if we want to do the English class scores on their tests or whatever, here's the English class, here's the history class, and you can see 4 in the 40s. Well, history class didn't have anybody in the 40s. English class had somebody at 45. For the 50s is what this stands for. History class had a 59, English class had a 57. In the 60s, history class had a 61 and a 67. English had a 62, 66, 68, and 69. So in the lower scores, there's a lot more from the English class. As we get to the upper scores, in the 80s, there's a lot more over here in the history class. There's 1, 2, 3, 4, 5, 6 of them, but there's only 3 in the 80s for the English class. Same for the 90s. There's 3 in the 90s and only 1 for the English class. There was actually a 100. That 0 means that 10 and 0 make a 100. There was actually a 100% in the history class and no 100% in the English class. Constructing a dot plot. A dot plot is basically starting with just a number line, where we have to go from our smallest possible value up to our largest possible value, and just put a dot above the value as we come across them, just like kind of putting tallies. So we construct that number line and put a dot above each value as we hit it, going vertically up if we repeat. So like here, we went from 0 to 16, because those are all the possible values. We had a 0, so we put a dot above the 0, a 2, a 10, so put a dot above the 10, a 2, so there's already a dot there, so put this dot above it, 5, a 3, a 1, another 2, so we keep going up, another 2, keep going up, and you fill in the dots. And you can see that gives you almost like a bar graph as well. The heights move up. So similar to the stem and leaf plot, the heights move up. But a dot plot only works for discrete data, where the stem and leaf plot will kind of groups the data together for you for some of the continuous data. So again, you can get the shape, similar like the histogram, and get a shape. This is skewed to the right. It's kind of bell-shaped, but it's stretched out to the right side. So time series plot. A time series plot, rather than looking at several different characteristics and comparing them at the same point in time, we're looking at a single value and how it changes over time. So here we're going to look at, this is showing the Dow Jones Industrial Average, starting in the year 2000, going up to the year 2009. So we're going to set this up. Our years, or our times, whether it's months, years, days, or whatever, go across the bottom, always, in a time series plot. And then the axis here has to include from our smallest value up to our largest value. Then we put dots above each of the time periods. And then we can connect those dots. What you see here is these dots show us where the line is the steepest. First of all, it shows us where it's increasing. Here it's increasing here, 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 and here. Those are the spots where it's increasing. It's decreasing, of course, here, 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 here. That's it. Those are the spots where it's going down, sloping down. You can tell what's increasing the most is here, because that's when it's going up the steepest. Decreasing the fastest, here, because that's where it's going down the steepest. On the TI to make a line graph, we put in our years in one. I'll go to the TI here quick. Go to Stat, Edit, and Edit again. Go up and hit Clear, Enter to clear out L1. So I'll put in 2000, 2001, 2002, 2003. That's as far as I'm going to go here for our example. Arrow over to the L2. I'm going to put in the 10787, 10022, 8341.6 and 10454 are my values. So now I'm going to get out of here. I'm going to second quit. I'm going to go to second stat plot here, my y equals. And now in the first plot, I'm going to select the first plot. I'm going to change the type to the second type, which is the line graph. I select that. L1 and L2 for my X list and Y list. My type of mark is selected there. Doesn't really matter which one I have. That one's probably the most visible. So now I have them in, and I'm going to zoom again. Zoom 9 is my stat zoom. I'm just pushing them under. I'll show you a zoom stat. So zoom 9, and there's my line plot. Now remember, I only put in the first 4 numbers, so you're only getting the first little part of this, which it does look like that. It's just the rest of that's missing because I didn't enter those into my calculator. So there we've learned how to construct stem and leaf, dot plots, and time series plots. We've seen on the calculator the histogram and the line plot. That is the end of section 3 of chapter 2. So I'm going to go ahead and pause again and switch. Now section 4 here of chapter 2 is to me one of the most important things you can learn in statistics. Statistics can be used to mislead, and graphs can be created in such a way as to be misleading. Now I want to look at some of those examples here. We're going to hear how to properly position a graph so it's not to be misleading, or how to position it so it could be misleading if you wanted to. Understand the area principle, how you can use other dimensions to create areas that make it misleading, and understand how three-dimensional graphs can be misleading. So first, let's look at positioning on the vertical scale. Statistical graphs, when properly used for communication, they communicate data honestly, but unfortunately, they can be accidentally or intentionally used to misrepresent data, to stretch it a little bit to make it fit what somebody else wants it to. It's still throwing out accurate numbers, but the appearance is misleading. So 3 of the most common ways of doing that. One is to position the vertical scale, and we'll look at that. Another is sizing the images differently, and another is misleading perspective or angles or 3 dimensions. So here, what was done on this one, as you can see, it started, instead of starting at 0, it started at 35 and went up. So it makes it look like there's quite a bit of difference here from 2002 to 2004. However, if we had started at 0, you can see here there is very little change from 2002 to 2008. You can see here, it went from there to there. That's not a large increase. But if we start at 35 instead of 0, it looks like we go from here all the way up here. It's several times larger by just the size of the bars. Even if you do catch this and see that, oh, it didn't start at 0, it's still visually, your mind wants to say, wow, it's a huge increase. When really it isn't. It's just over a 10,000 increase is all it is. So from 36 or 37 up to like a 48 or so, it looks like. So the area principle. When amounts are compared by constructing an image for each amount, the areas of the images must be proportional to the amounts. You can't play with the widths or the depths or anything like that. So let me show you what I mean here. This is an honest graph. The width of the bars are the same. The height is what is representing the change, 90 cents here and 316 here. So is an honest. This one is just over 3 times the size. It's only 3 times the height. It's just over 3 times the value. But if we mess with it like this, now this looks like it's a lot bigger. But all that's happened here, we're still just looking at a baseline here and a height. The height of this one is more than 3 times as much. But we got the length and everything else thrown in there. It looks like it's like 9 times the size because of the area. So don't use area. You can only use a single dimension to represent values. Don't try to make it 2-dimensional. That's misleading. Also, 3-dimensional graphs, like here, you have depth to it. This is a little bit misleading because, and this one's actually relatively accurate. But this one's a little bit misleading because it's not necessarily flat across here. A lot of these are angled here. So this one's starting out lower so you don't get the height. You also have to look at the reflection on the back wall with the lines. You can't just trace this straight across because this axis may or may not be right on. You can see this actually should stay below 3. So it should come over like that, by the way it looks to me. So those are our 3 most common forms of misrepresentation. Not starting at 0 on the vertical axis. I was messing with the vertical axis. Violating the area principle. Or using 3 dimensions. 3 dimensions just can be very deceiving because of the way they're made. All these things, and there are a lot of others we're going to come up with when we start talking about numerical representations of data in next week. A lot of things, little tricks people can use in statistics to try to mislead a little bit. And in advertising and stuff like that, that's part of their efforts. Politics, misleading statistics are everywhere. In fact, there's a lot of just made up statistics in politics as well. But we'll talk about those more in the numerical side. So that is about it for our week 2 data, or information for chapter 2. So I'm going to end this recording. If you have any questions, let me know and I will get back to you as soon as I can. Otherwise, have a great week.